Flow control and congestion control are two important mechanisms that characterize the TCP transport protocol. Basically, referring to the flow control, in this case, the receiver is authorizing the sender based on the current storage capability. This means that since the receiver has a buffer with a certain capacity, then based on the state of the buffer, the receiver will tell the sender what is the amount of information that the sender can send or transmit to the receiver. Similarly, when we talk about the congestion control, the sender will adapt the transmission rate according to the current state of the network. The flow control itself is not sufficient. It depends only on the receiver's capacity to receive more or less information, but is not sufficient to prevent a congestion in the network. In fact, in this regard, even lower layers of the TCP IP protocol stack are not sophisticated enough to handle scenarios of congestion control, and hence the task of handling congestion control has been dedicated or handed to the TCP as the main transport protocol. TCP itself is implemented on hosts and hence allows to do the congestion control task in an end-to-end fashion. So in order to define how to handle congestion control, it's important to also identify what do we mean by the congestion event. We say that a congestion event will occur when the transmission rate causes a congestion on a link. In this example, we see two users that are connected to two servers through a common link between the two. We say that the link is congested when the sum of the transmission rates, defined as Ri, is greater than the capacity of the link, which is denoted by C. The natural way for the TCP to control the rate at which the data is transmitted into the network by the transmitter is by adjusting what is known as the transmission window. We will denote this transmission window as SWND, which basically represents this transmission window. And also the transmitter will maintain a congestion window defined as or denoted as CWND, which will basically vary based on the events that it observes. So previously we had defined the receiving window. Now we have defined the congestion window, which characterizes the transmitter, and we have also defined the transmission window, which is a main characteristic of the TCP control protocol, which allows to also handle congestion control. So at any given time, the transmitter's window, which we defined as SWND, is sized according to a given set of values. And we say that it depends on the receiving window, defined as RWND, which is basically determined by the receiver's capability to receive more or less information, by the congestion window, which we just defined in the previous slide, which basically is determined by the transmitter. So we say that the transmitter's window, SWND, will be equal to the minimum between the receiving window and the congestion window. So whichever of the two has the lower value, that will be the value that determines the transmitter's window denoted as SWND. So the questions that we want to address are how to adjust the congestion window and also how to detect when there is a congestion. So we defined before what is a congestion event. Formally, we can say that the congestion event will happen when we have a loss of a segment, because packets at the transport layer are referred to as segments. So if there is a loss of a segment, And then there is a timeout that happens because the receiver has not sent an acknowledgement within a given amount of time. Then we say that we are seeing or we are experiencing a congestion event. In this case, the reaction to this congestion event will be to reduce the size of the congestion window. And this is important because for a lower value of the congestion window, as we saw on the previous slide, then the transmitter's window will be adjusted accordingly. The value of this congestion window, since we are talking about the congestion control of the TCP, will be updated by the TCP transmitter. However, this depends on the phase in which the transmitter is, or basically on the state in which the transmitter happens to find itself. So based on this, we define two main states or phases, which we denote as slow start or congestion avoidance. So in order to determine if we are in a slow start or in a congestion avoidance state, there needs to be met some set of conditions. So to do this, we define a threshold, which we denote as SS thresh, which is preset, which will basically be managed by the TCP entity at the transmitter side. If the congestion window, which we have defined previously, is lower than this threshold, which we have called SS thresh, then we say that the transmitter is in the slow start phase. If instead the congestion window is greater than this SS threshold, then the transmitter is in the congestion avoidant phase. Now we will go and look at how the TCP transmitter will basically update the congestion window CWND when it finds itself in the slow start phase. So at the beginning, the default value of the congestion window is set to one maximum size segment, so one MSS. And usually the SS threshold is set to a much higher value. So by default in the beginning, the congestion window will be lower than the SS threshold, and hence we start in the slow start phase. However, there are certain rules according to which the congestion window will be increased according to the state of the network. So what is the rule for increasing the congestion window in slow start? The simplest way of putting it is that the congestion window will be incremented by one MSS for each acknowledgement that it receives. What does this mean? We start with a window of one MSS. When along the round trip time, the receiver has sent the acknowledgement message, then in the next step, the congestion window will be equal to 2. This because it is already equal to 1, plus if it receives an acknowledgement of the message that has been sent in the prior step, then it updates it equal to 2. In the same way, once the congestion window is equal to 2 MSSs, so in this case we have denoted as 2W, then in the next step, for each of the MSSs that it sends, if it receives an acknowledgement message for each of them, then the value of the congestion window will be doubled and equal to 4. The same thing is also said here. So basically, one segment is sent, and after an interval which is equal to the round trip time which has been previously defined, the acknowledgement is received. In this case, the congestion window is set to 2, so we are in this state, and 2 segments are sent. After receiving the 2 acknowledgements, the congestion window will be set to 4, and so on and so forth. So the increase, we notice that it is an exponential increase of the congestion window. To illustrate this way how the congestion window increases, we see a illustrative example. So basically, we start with a congestion window equal to 1. this congestion window equal to 1 means that there is one segment which is sent from the transmitter to the receiver. When the segment is sent from the receiver side, there will be an acknowledgement message which is sent back to the transmitter. For the sake of the argument, we have assumed that the acknowledgements have negligible duration. Now, in the next step, the congestion window will already have the segment size of 1 plus the one acknowledgement message that it has received, so hence the value of the congestion window will be equal to 2. In the same way, when in the next step, the congestion, or in the next transmission, the congestion window sends 2 segments, then for each of these segments, there will be a corresponding acknowledgement message that will be sent from the receiver towards the transmitter. In this case, in the next transmission, the transmitter has already set the size of the window equal to 2, plus the 2 acknowledgement messages that it receives allows him to understand that the congestion window can be updated to 4. And the same way when we have 4 segments that are transmitted, each of them has a corresponding acknowledgement message that gets transmitted from the receiver towards the transmitter, and hence the value of the congestion window is equal to 8. So to summarize, we can say that the increase of the window when we are in the slow start state of transmission has an exponential increase. Contrary to what the name might suggest, this means that the increase of the congestion window is not slow, but rather happens in an exponential fashion.